In the vast cosmic ocean containing over 2 trillion galaxies, each harboring billions of stars, there exist celestial objects so rare that finding them is like discovering a single grain of diamond sand on all the beaches of Earth. Tonight, we're embarking on a journey to explore the universe's most extraordinary stellar phenomena, stars so unusual that some exist in numbers you could count on your fingers, while others challenge everything we thought we knew about how the cosmos works. And I'd love to know where in the world you're joining me from and what time it is there right now. Drop a comment below. There's something magical about knowing we're exploring the universe together across different continents and time zones. Now let's get started. Let's begin with a star that shouldn't exist according to our current understanding of stellar evolution. In 2014, astronomers using the Subaru telescope in Hawaii discovered SMJ 313, a star with virtually no heavy elements. This ancient giant contains less iron than a paperclip, making it one of the most metal-poor stars ever found. To understand why this discovery is so remarkable, we need to journey back to the beginning of time itself. In the first few minutes after the Big Bang, the universe contained only hydrogen, helium, and trace amounts of lithium. Every other element, the carbon in your body, the oxygen you breathe, the iron in your blood, was forged in the nuclear furnaces of stars and scattered through space when those stars died. The first generation of stars, called Population 3 stars, were massive giants composed entirely of primordial hydrogen and helium. These stellar titans lived fast and died young, exploding as supernovae and enriching the cosmos with the first heavy elements. But here's the mystery. We've never actually observed a Population 3 star. They should have all died billions of years ago, yet SMSS J031300.36 seems to be a survivor from this ancient era. This stellar fossil tells us a story about the early universe that we're only beginning to understand. Its chemical composition suggests it formed from gas clouds that were barely touched by the first generation of stellar explosions. Finding such a star is like discovering a living dinosaur. It gives us a direct window into cosmic conditions that existed over 13 billion years ago. The European Southern Observatory's Very Large Telescope has been instrumental in studying these ancient stellar relics. By analyzing the light from these stars through spectroscopy, astronomers can read their chemical fingerprints like cosmic DNA, revealing the conditions that existed when they formed. Each spectrum tells a story of stellar nucleosynthesis, galactic chemical evolution, and the gradual enrichment of the universe with the elements necessary for planets and life. But metal-poor stars aren't the only rarities in our cosmic neighborhood. Consider the magnetars, neutron stars with magnetic fields so intense they defy comprehension. The strongest magnetic field ever created in a laboratory is about 45 Tesla. A typical refrigerator magnet produces about 5/1000ths of a Tesla. A magnetar's magnetic field can reach 100 trillion Tesla, strong enough to strip the electrons from atoms at a distance of 1,000 kilometers. Only about 30 magnetars have been confirmed in our galaxy, making them incredibly rare cosmic phenomena. These stellar remnants are born when massive stars collapse, concentrating the mass of our Sun into a sphere just 20 kilometers across, while amplifying magnetic fields to unimaginable strengths. The magnetic field of a magnetar is so powerful that it warps the very atoms around it, creating conditions that exist nowhere else in the universe. SGR 1900+14, discovered in 1979, was the first confirmed magnetar. This cosmic lighthouse occasionally produces giant flares that release more energy in 1/10 of a second than our Sun produces in 100,000 years. The December 27, 2004 flare from SGR 1806-20 was so intense it temporarily blinded satellites and affected Earth's ionosphere from a distance of 50,000 light-years. If you're finding these cosmic extremes as fascinating as I am, I'd really appreciate it if you could hit that subscribe button and give this video a thumbs up. We're exploring some of the universe's most incredible phenomena together, and your support helps me continue bringing these amazing discoveries to light. There's so much more cosmic wonder ahead. The rarity of magnetars stems from the precise conditions required for their formation. Not every massive star becomes a magnetar when it dies. The star must have the right mass, rotation rate, and magnetic field strength during its lifetime. Most neutron stars have magnetic fields millions of times weaker than magnetars, making these ultramagnetic objects truly exceptional. Thorn-Zitko objects represent another class of stellar impossibility. These hypothetical stars consist of a neutron star core surrounded by a normal stellar envelope, essentially a star within a star. The concept was proposed by physicist Kip Thorne and astronomer Anna Zitko in 1975, but finding one proved incredibly challenging. In 2014, astronomers announced the discovery of HV 2112, a red supergiant in the Small Magellanic Cloud that might be our first confirmed Thorn-Zitko object. This bizarre stellar hybrid shows unusual chemical signatures that could only be produced by nuclear reactions occurring around a neutron star core. The discovery suggests that these cosmic chimeras might actually exist, though they remain extraordinarily rare. The formation of a Thorn-Zitko object requires a neutron star to somehow end up inside another star, perhaps through a close encounter in a binary system or a direct collision. The neutron star's immense gravity would disrupt normal stellar structure, while its surface temperature of millions of degrees would drive exotic nuclear reactions in the surrounding stellar material. Blue stragglers present another stellar mystery that has puzzled astronomers for decades. These stars appear younger and bluer than they should be based on their location in star clusters. In a typical cluster, all stars form at roughly the same time from the same gas cloud. The most massive stars should evolve fastest, becoming red giants, while smaller stars remain on the main sequence. But blue stragglers seem to have found a fountain of youth, appearing more massive and younger than their cluster companions. The leading explanation involves stellar cannibalism. These stars have gained mass by merging with companions or stripping material from nearby stars. This cosmic vampirism allows them to burn brighter and live longer than single stars of their original mass. The Hubble Space Telescope has been crucial in studying blue stragglers, providing the resolution needed to identify these unusual objects in crowded star clusters. Observations of globular clusters like 47 Tucani and Omega Centauri have revealed populations of blue stragglers that tell stories of stellar interactions and evolution in dense stellar environments. Carbon stars represent another rare stellar type that showcases the universe's chemical diversity. These cool giants have atmospheres rich in carbon rather than oxygen, creating conditions where carbon compounds like graphite and silicon carbide can condense into dust grains. The result is a star that appears distinctly red and is surrounded by sooty clouds of carbon-rich material. Our Corona Borealis stars take carbon enrichment to an extreme. These hydrogen-deficient giants are thought to be the products of white dwarf mergers, creating stars with surface compositions unlike anything else in the galaxy. Fewer than 100 Corona Borealis stars are known, making them among the rarest stellar types. These peculiar stars undergo dramatic declines in brightness when carbon dust condenses in their atmospheres, temporarily obscuring their light. The star Corona Borealis itself can fade by 9 magnitudes, becoming 6,000 times dimmer before slowly returning to its normal brightness as the dust disperses. Wolf-Rayet stars represent the final, spectacular phase of evolution for the most massive stars in the universe. These stellar powerhouses have shed their outer hydrogen layers, revealing cores that burn helium and heavier elements at temperatures exceeding 100 million degrees. Their powerful stellar winds, moving at speeds up to 5,000 kilometers per second, create some of the most beautiful nebulae in the cosmos. Only about 600 Wolf-Rayet stars are known in our galaxy, making them incredibly rare despite their enormous luminosity. These stellar furnaces burn so intensely that they consume their nuclear fuel in just a few million years before exploding as supernovae or collapsing into black holes. The WR104 star, located in the constellation Cygnus, exemplifies the extreme nature of Wolf-Rayet stars. This stellar giant has a surface temperature of 50,000 Kelvin, nearly 9 times hotter than our Sun, and shines with the luminosity of 500,000 suns. Its powerful stellar wind creates the spectacular Crescent Nebula, a cosmic bubble of glowing gas expanding at 30 kilometers per second. What makes Wolf-Rayet stars so rare is the precise evolutionary pathway required to create them. Only stars born with masses exceeding 25 times our Sun can become Wolf-Rayet objects, and they must lose enormous amounts of mass through stellar winds during their lifetimes. This mass loss strips away the hydrogen envelope, revealing the nuclear-burning core beneath. The chemical signatures of Wolf-Rayet stars tell fascinating stories about stellar nucleosynthesis. Their spectra show strong emission lines from highly ionized carbon, nitrogen, and oxygen, elements forged in the star's core and brought to the surface by convection and mass loss. These stars are cosmic factories, producing and dispersing the heavy elements essential for planet formation and life. Luminous blue variables represent another category of stellar extremes that push the boundaries of what's physically possible. These massive, unstable stars undergo dramatic eruptions that can temporarily make them among the brightest objects in their host galaxies. Eta Carinae, perhaps the most famous example, ejected several solar masses of material during its great eruption in the 1840s. The homunculus nebula surrounding Eta Carinae preserves the record of this spectacular outburst. Hubble Space Telescope observations reveal a bipolar structure of expanding gas and dust, moving at speeds exceeding 600 kilometers per second. The nebula contains enough material to make several stars like our Sun, all ejected by a single stellar tantrum. Only a few dozen luminous blue variables are known throughout the local group of galaxies. These stellar monsters exist at the very edge of stability, where radiation pressure from their intense nuclear burning nearly overcomes their own gravity. They represent stars in crisis, struggling to maintain their structure while burning nuclear fuel at prodigious rates. The Pistol star, discovered by the Hubble Space Telescope in 1997, was once thought to be one of the most massive stars known. Located near the center of our galaxy, this luminous blue variable has a luminosity 10 million times greater than our Sun. Its powerful stellar wind has created the Pistol Nebula, a shell of ionized gas 4 light-years across. Speaking of cosmic rarities, if you're fascinated by these stellar extremes, you should definitely check out my video on the rarest object in the universe. It explores phenomena so unusual that they challenge our understanding of physics itself, objects that make even these rare stars seem common by comparison. The universe has a way of creating things that shouldn't exist according to our theories. The link is in the description and pinned on the comments. But let's continue our exploration of stellar oddities with the mysterious Przybylski star. Discovered in 1961 by Polish-Australian astronomer Antoni Przybylski, this peculiar object contains elements that shouldn't exist in stellar atmospheres. Spectroscopic analysis reveals the presence of short-lived radioactive elements like actinium, holmium, and even possible traces of superheavy elements. The puzzle of Przybylski's star deepens when we consider that these radioactive elements have half-lives measured in days or years, not the millions of years required for stellar evolution. How can a star maintain concentrations of elements that should decay almost immediately? Some astronomers have proposed exotic explanations, including the possibility that the star is somehow producing these elements through unknown nuclear processes. The AP stars, or chemically peculiar A-type stars, represent a broader class of stellar anomalies. These objects show unusual abundances of elements like strontium, chromium, and rare earth metals in their atmospheres. The abundance patterns suggest that atomic diffusion, the separation of elements by atomic weight in the star's magnetic field, creates chemical stratification unlike anything seen in normal stars. HD 101065, another chemically peculiar star, shows extreme overabundances of mercury and manganese while being severely depleted in helium. These abundance anomalies create atmospheric conditions so unusual that they challenge our understanding of stellar physics and atomic processes in extreme environments. Neutron stars themselves represent some of the most extreme objects in the universe, but even among these stellar remnants, some are extraordinarily rare. Millisecond pulsars, neutron stars spinning hundreds of times per second, were once thought impossible. The first millisecond pulsar, PSRB 1937+21, was discovered in 1982 and revolutionized our understanding of neutron star physics. These cosmic lighthouses achieve their incredible rotation rates through a process called recycling. In binary systems, material from a companion star can spin up an old, slowly rotating neutron star, accelerating it to millisecond periods. The process requires precise conditions. The mass transfer rate must be just right to spin up the neutron star without causing it to collapse into a black hole. PSRJ 1748-2446 AD, located in the globular cluster Terzan 5, holds the record as the fastest spinning neutron star known, rotating 716 times per second. At this rate, the star's equator moves at roughly 24% the speed of light, approaching the theoretical limit where centrifugal forces would tear the neutron star apart. The discovery of double pulsar systems represents another pinnacle of stellar rarity. PSR J0737-3039A and B, discovered in 2003, consists of two neutron stars orbiting each other every 2.4 hours. This system provides an unprecedented laboratory for testing Einstein's theory of general relativity and studying gravitational wave emission. Only one double pulsar system is known in our galaxy, making it literally one of a kind. The two neutron stars are spiraling closer together due to energy loss through gravitational waves, and they will eventually merge in about 85 million years. When they do, the collision will create gravitational waves detectable by observatories like LIGO and Virgo. Quark stars represent a hypothetical type of stellar remnant that might exist beyond neutron stars. If matter is compressed beyond nuclear density, protons and neutrons might break down into their constituent quarks, creating a quark-gluon plasma. These exotic objects would be even denser than neutron stars, with properties that push the boundaries of known physics. RX J18565-3754, a compact object in the constellation Corona Australis, has been proposed as a possible quark star candidate. Its small radius and high temperature don't match theoretical predictions for neutron stars, suggesting it might be composed of exotic quark matter. However, the identification remains controversial, and no quark stars have been definitively confirmed. Strange stars, composed of strange quark matter, represent another theoretical possibility for ultradense stellar remnants. These objects would be even more exotic than quark stars, containing roughly equal numbers of up, down, and strange quarks in a stable configuration. The surface of a strange star would be a crystalline crust of ordinary matter just centimeters thick, overlying an ocean of liquid quark matter. Population 3 stars, the first generation of stars in the universe, remain among the most sought-after objects in astronomy. These primordial giants, composed entirely of hydrogen and helium from the Big Bang, should have masses hundreds of times greater than our Sun. Their nuclear burning would have been so intense that they lived for only a few million years before exploding as parent stability supernovae. The James Webb Space Telescope is actively searching for population 3 stars in the most distant galaxies, looking for the distinctive spectral signatures of hydrogen and helium burning without heavy elements. Finding even one of these stellar fossils would provide direct evidence of the universe's first stars and the beginning of cosmic chemical evolution. Hypervelocity stars represent another rare stellar phenomenon that challenges our understanding of galactic dynamics. These cosmic speedsters travel at velocities exceeding the escape speed of our galaxy, racing through space at speeds up to 1,700 kilometers per second. Most hypervelocity stars are thought to be ejected from the galactic center through gravitational interactions with the supermassive black hole Sagittarius A star. HVS-1, the first confirmed hypervelocity star, was discovered in 2005 by the MMT Observatory. This B-type star is traveling at 850 kilometers per second, fast enough to escape the Milky Way entirely. Its trajectory can be traced back to the galactic center, supporting the theory that it was ejected through a gravitational slingshot mechanism. The Hills mechanism, proposed by astronomer Jack Hills in 1988, explains how binary star systems can be disrupted by close encounters with supermassive black holes. One star is captured into a tight orbit while its companion is flung away at tremendous speed, becoming a hypervelocity star racing through the galaxy. S5HVS1, discovered in 2019, holds the record as the fastest-moving star known, traveling at 1,755 kilometers per second. This star was likely ejected from the galactic center just 5 million years ago and is now racing toward the constellation Grus, destined to escape our galaxy and wander through intergalactic space. The discovery of hypervelocity stars has opened new avenues for studying galactic structure and the properties of supermassive black holes. These stellar refugees carry information about conditions in the galactic center and provide unique probes of the Milky Way's gravitational potential. The study of hypervelocity stars has revealed unexpected diversity in their origins and properties. While most are thought to originate from the galactic center, some hypervelocity stars show chemical compositions suggesting they formed in the galactic disk or halo. This has led astronomers to propose alternative ejection mechanisms, including supernova explosions in binary systems and interactions with intermediate-mass black holes. US 708, discovered by the Sloan Digital Sky Survey, represents a particularly intriguing case. This red giant star is moving at over 500 kilometers per second, but its chemical composition suggests it formed in the outer regions of our galaxy rather than near the central black hole. The mystery of how this star achieved such high velocity without a galactic center origin continues to puzzle astronomers. The Gaia space mission has revolutionized the search for hypervelocity stars by providing precise measurements of stellar positions and velocities for over 1 billion stars. This unprecedented dataset has revealed that hypervelocity stars are more common than previously thought, with dozens of candidates identified throughout the galaxy. Subdwarf B stars represent another class of stellar oddities that challenge conventional understanding of stellar evolution. These hot, compact objects have somehow lost nearly all their hydrogen envelopes, leaving behind cores that burn helium at temperatures exceeding 20,000 Kelvin. The mechanism responsible for stripping away their outer layers remains one of astronomy's unsolved puzzles. HD 49798, a subdwarf B star in the constellation Draco, exemplifies the extreme nature of these objects. With a surface temperature of 35,000 Kelvin and a mass just half that of our Sun, it represents a stellar configuration that shouldn't be stable according to standard stellar evolution models. Yet hundreds of these objects exist, suggesting we're missing something fundamental about how stars evolve. The binary evolution channel offers one explanation for subdwarf B formation. In close binary systems, mass transfer or common envelope evolution might strip away the hydrogen envelope just as the star begins burning helium in its core. This process requires exquisite timing and specific orbital configurations, explaining why subdwarf B stars are relatively rare. Helium flash events, which occur when helium ignition begins explosively in low-mass stars, might also play a role in creating subdwarf B stars. If the helium flash is particularly violent, it could potentially eject the entire hydrogen envelope, leaving behind a naked helium-burning core. However, the details of this process remain poorly understood. Central stars of planetary nebulae represent the final evolutionary stage for stars like our Sun, but some of these objects display properties that defy explanation. The central star of the Stingray Nebula, for example, has evolved from a cool giant to a hot white dwarf in just 20 years, a transformation that should take thousands of years according to stellar evolution theory. SEO 244567, the central star of the Stingray Nebula, has increased in temperature from 21,000 to 60,000 Kelvin since 1971. This rapid evolution suggests that stellar death can sometimes proceed much faster than our models predict, challenging our understanding of the final stages of stellar life. The Wolf-Rayet central stars of planetary nebulae represent an even rarer subset of these evolved objects. These stars have somehow retained enough mass after the planetary nebula ejection to continue burning helium and heavier elements in their cores. Only a handful of such objects are known, making them among the rarest stellar types in the galaxy. PG 1159-035, a Wolf-Rayet central star, shows spectral features indicating ongoing nuclear burning of carbon and oxygen in its core. This suggests that some planetary nebula central stars can continue evolving rather than simply cooling as white dwarfs. opening new questions about the diversity of stellar endpoints. AM Canum Venaticarum stars represent a bizarre class of binary systems where helium-rich material is transferred between two white dwarf stars. These systems have orbital periods measured in minutes rather than hours or days, with the two stellar remnants orbiting so close together that they would fit inside our Sun. The prototype AM-CVN has an orbital period of just 17 minutes, making it one of the shortest period binary systems known. The primary white dwarf accretes helium-rich material from its companion, occasionally undergoing thermonuclear explosions that create helium novae, stellar explosions powered by helium fusion rather than hydrogen burning. These ultra-compact binaries are thought to be progenitors of Type I supernovae, the stellar explosions used as standard candles for measuring cosmic distances. Understanding their evolution is crucial for cosmology, yet fewer than 50 AM-CVN systems are known throughout the galaxy. GP-COM, another AM-CVN system, has an orbital period of just 46 minutes and shows evidence for ongoing mass transfer between its two white dwarf components. The system is slowly losing energy through gravitational wave emission, causing the orbit to decay and the mass transfer rate to increase over time. The discovery of these ultra-compact binaries has opened new windows into white dwarf physics and binary evolution. The extreme conditions in these systems, with orbital velocities reaching thousands of kilometers per second and mass transfer rates that can vary dramatically over time, create natural laboratories for studying matter under conditions impossible to reproduce on Earth. Cataclysmic variables represent a broader class of interacting binary systems, but some display properties so unusual that they challenge our understanding of stellar physics. Polars, for example, are white dwarf stars with magnetic fields so strong that they completely disrupt the normal accretion disk formation process. AM Hercules, the prototype polar, has a magnetic field strength of 230 million Gauss, roughly 100 million times stronger than Earth's magnetic field. This intense magnetism channels accreting material directly onto the white dwarf's magnetic poles, creating hotspots that emit X-rays and cyclotron radiation. The synchronization between the white dwarf's rotation and the binary orbital period in polars creates a unique astrophysical environment. The magnetic field is so strong that it locks the white dwarf's rotation to the orbital motion, creating a system where the same magnetic pole always faces the companion star. Intermediate polars represent a related but distinct class of magnetic cataclysmic variables where the white dwarf's magnetic field is strong enough to disrupt the inner accretion disk, but not strong enough to prevent disk formation entirely. These systems show complex periodicities as the magnetosphere interacts with the accretion flow in ways that are still being studied. DQ Hercules, discovered as a nova in 1934, is now known to be an intermediate polar with a white dwarf rotation period of 71 seconds. The system shows X-ray pulsations as hot material impacts the white dwarf's magnetic poles, creating a cosmic lighthouse effect that repeats with each rotation. The study of magnetic cataclysmic variables has revealed the incredible diversity of white dwarf magnetic fields and their effects on binary evolution. These systems provide unique insights into the physics of accretion in strong magnetic fields and the long-term evolution of close binary systems. Symbiotic stars represent another rare class of interacting binaries where a white dwarf accretes material from a red giant companion. Unlike cataclysmic variables, symbiotic stars have much wider orbits and lower mass transfer rates, creating a different type of stellar interaction. Z Andromedae, the prototype symbiotic star, undergoes periodic outbursts as the white dwarf accumulates enough material to trigger thermonuclear burning on its surface. These outbursts can increase the system's brightness by several magnitudes and last for months or years, creating spectacular displays of stellar violence. The Mira variables represent a class of pulsating red giant stars that undergo dramatic changes in brightness over periods of months to years. While Mira variables themselves are relatively common, some display properties that make them truly exceptional among stellar objects. Chi Cygni, one of the most extreme Mira variables, can vary in brightness by a factor of 15,000 over its 409-day pulsation cycle. At maximum light, this star shines with the luminosity of 9,000 suns, while at minimum it becomes virtually invisible to the naked eye. The pulsation mechanism in Mira variables involves complex interactions between stellar structure, nuclear burning, and atmospheric dynamics. As these evolved giants expand and contract, they create shock waves that propagate through their extended atmospheres, driving mass loss and creating the spectacular variability we observe. Our Aquarii represents a symbiotic Mira variable, a system where a pulsating red giant transfers material to a white dwarf companion. The combination of Mira pulsations and symbiotic activity creates one of the most complex and beautiful stellar systems known, with jets, shock fronts, and ionized gas structures extending over several light years. The Hubble Space Telescope has revealed the intricate structure surrounding our Aquarii, showing a complex network of knots, jets, and shock fronts created by the interaction between the Mira variables' stellar wind and material ejected during symbiotic outbursts. This cosmic sculpture, spanning over a light year, represents one of the most beautiful examples of stellar interaction in our galaxy. The jets emanating from our Aquarii travel at speeds exceeding 700 kilometers per second, creating bow shocks as they plow through the surrounding interstellar medium. These high-velocity outflows suggest that the white dwarf component occasionally undergoes nova-like explosions, ejecting material in collimated beams that carve through space, like cosmic blowtorches. Sakurai's object, discovered in 1996, represents one of the most remarkable stellar transformations ever observed. This star underwent a late helium flash that caused it to expand from a hot white dwarf back into a cool giant in just a few years, a process that normally takes thousands of years and had never been observed in real time. The rapid evolution of Sakurai's object has provided astronomers with a unique opportunity to study stellar physics in action. Spectroscopic observations have tracked the star's changing surface composition as nuclear burning products are dredged up from the interior, revealing the complex interplay between nuclear physics and stellar structure. Within just a few years, Sakurai's object transformed from a hydrogen-rich star to one dominated by helium and carbon, then became shrouded in dust as carbon condensed in its cooling atmosphere. This dramatic metamorphosis compressed millions of years of normal stellar evolution into a human lifetime, offering unprecedented insights into stellar death and rebirth. FG Sagittae represents another example of rapid stellar evolution, though in this case the transformation has been ongoing for over a century. This star has evolved from a hot subdwarf to a cool giant while astronomers have been watching, providing a real-time view of stellar evolution that was previously only theoretical. The central star of the planetary nebula Abell 78 has undergone a similar transformation, cooling from 60,000 Kelvin to just 4,000 Kelvin over the past century. These rapid evolutionary changes challenge our understanding of stellar physics and suggest that the final stages of stellar life can be far more dynamic than previously thought. Born-again episodes in planetary nebula central stars represent another rare phenomenon where stars that have already shed their envelopes undergo additional helium flashes. These late thermal pulses can cause the star to expand again, potentially creating multiple shells of ejected material around the central object. Abell 30 and Abell 58 are examples of planetary nebulae that show evidence for born-again episodes. These objects display complex, multi-shell structures that record the history of multiple mass loss events, creating some of the most intricate and beautiful structures in the cosmos. The Stingray Nebula itself represents the youngest known planetary nebula, having formed within the past few decades. Its central star's rapid evolution from cool giant to hot white dwarf has been accompanied by the ionization of previously ejected material, creating a nebula that is literally forming before our eyes. Our Coronae Borealis stars represent one of the most mysterious classes of variable stars, undergoing dramatic declines in brightness when carbon dust condenses in their atmospheres. These hydrogen-deficient giants are thought to be the products of white dwarf mergers, creating stars with surface compositions unlike anything else in the galaxy. The prototype, our Coronae Borealis, can fade from 6th magnitude to below the limit of naked eye visibility in just a few weeks, remaining faint for months or years before slowly returning to its normal brightness. This dramatic variability is caused by the formation of carbon clouds in the star's atmosphere, which absorb and scatter the star's light. Fewer than 100 Arcturone borealis stars are known throughout our galaxy and the Magellanic Clouds, making them among the rarest stellar types. Their extreme hydrogen deficiency and unusual chemical compositions suggest they form through a very specific evolutionary pathway that occurs only under exceptional circumstances. The double degenerate scenario for our CRB formation involves the merger of two white dwarf stars, one composed primarily of helium and the other of carbon and oxygen. The merger process would create a star with the observed chemical composition and mass, explaining both the hydrogen deficiency and the unusual abundance patterns. RY Sagittarii, another Arcturone borealis star, has been observed to undergo multiple decline events, each lasting different amounts of time and reaching different minimum brightnesses. These variations in the decline behavior suggest that the dust formation process is complex and depends on subtle changes in atmospheric conditions. The study of Arcturone borealis stars has implications for understanding type I supernovae, as the double degenerate merger scenario is also proposed as one pathway for producing these important stellar explosions. The existence of our CRB stars provides evidence that white dwarf mergers can occur and produce observable stellar remnants. Luminous red novae represent a recently recognized class of stellar explosions that are less energetic than supernovae but more powerful than classical novae. These events are thought to result from stellar mergers, creating transient objects that can briefly outshine entire galaxies before fading over months or years. V4044 Sagittarii, discovered in 2008, was the first galactic luminous red nova identified. This event reached a peak brightness of magnitude 9.4 and showed spectral features indicating the ejection of cool, dense material at relatively low velocities, characteristics that distinguish it from both novae and supernovae. The progenitor systems of luminous red novae are thought to be contact binaries or common envelope systems where two stars are spiraling together due to orbital decay. The final merger creates a brief but spectacular explosion as the two stellar cores combine and the merged object adjusts to its new configuration. V1309 Scorpii, another luminous red nova discovered in 2008, provided additional evidence for the stellar merger model. Pre-explosion observations showed a contact binary system with an orbital period of just 1.4 days, supporting the idea that these events result from the coalescence of close binary stars. The discovery of gravitational waves from merging neutron stars and black holes has opened new perspectives on stellar mergers and their observable consequences. While the mergers detected by LIGO and Virgo involve compact objects, the principles of orbital decay and coalescence apply to a wide range of stellar systems. Thorn-Zitko objects represent perhaps the most exotic type of stellar merger, where a neutron star becomes embedded within the envelope of a red supergiant. These bizarre hybrid objects would have the appearance of normal red giants, but with nuclear processes occurring around the central neutron star that could produce unique chemical signatures. HV2112, a red supergiant in the Small Magellanic Cloud, has been proposed as a candidate Thorn-Zitko object based on its unusual chemical composition. The star shows enhanced abundances of lithium, rubidium, and molybdenum that could be produced by nuclear reactions around a neutron star core. The formation of Thorn-Zitko objects requires a neutron star to somehow end up inside another star, either through a direct collision or through the evolution of a binary system where one component explodes as a supernova while the other survives. The resulting object would be unstable and short-lived, explaining why so few candidates have been identified. Yellow hypergiants represent another extremely rare class of massive evolved stars that exist in a narrow instability strip between red supergiants and Wolf-Rayet stars. These objects are so rare that fewer than a dozen are known in our galaxy, making them among the most exclusive stellar clubs in the cosmos. Rho Cassiopeiae, one of the most famous yellow hypergiants, has undergone dramatic changes in brightness and spectral type over the past century. In 2000, this star dimmed by over a magnitude and cooled significantly, ejecting a shell of material before returning to its previous state, behavior that demonstrates the extreme instability of these massive objects. The Pistol star, located near the galactic center, was once classified as a yellow hypergiant, but is now thought to be a luminous blue variable. This reclassification highlights the difficulty in understanding these rare, massive stars and the evolutionary connections between different types of stellar extremes. IRC plus 10420, another yellow hypergiant, is surrounded by a spectacular shell of dust and gas ejected during previous episodes of mass loss. The star's variability and mass loss history suggest it is in the final stages of evolution before becoming a Wolf-Rayet star or exploding as a supernova. The study of yellow hypergiants provides crucial insights into the evolution of the most massive stars in the universe. These objects represent a brief but important phase in stellar evolution, bridging the gap between red supergiants and the final explosive phases of massive stellar death. Blue supergiants in the local group represent some of the most massive and luminous stars known, but even among these stellar giants, some objects stand out as truly exceptional. The Pistol star, despite its reclassification, remains one of the most luminous stars in our galaxy, with a luminosity nearly 10 million times that of our Sun. Eta Carinae, perhaps the most famous luminous blue variable, continues to puzzle astronomers with its complex structure and violent history. The homunculus nebula surrounding this star contains clues to one of the most energetic stellar outbursts ever recorded, yet the mechanism responsible for the great eruption remains poorly understood. The binary nature of Eta Carinae, confirmed through X-ray observations and spectroscopic monitoring, adds another layer of complexity to this already mysterious system. The interaction between the two massive stars creates a colliding wind region that produces high-energy radiation and may have triggered the historical outbursts. The Eta Carinae system represents a cosmic time bomb, with both components destined to explode as supernovae within the next million years. The primary star, with an estimated mass of 90 to 120 times our Sun, exists at the very edge of stellar stability. Its companion, weighing in at 30 to 60 solar masses, is itself a massive star that would be considered extraordinary in any other context. Recent observations with the Hubble Space Telescope have revealed that Eta Carinae's great eruption in the 1840s ejected at least 10 solar masses of material at speeds exceeding 600 kilometers per second. This makes it one of the most energetic stellar events ever recorded, releasing more energy than a typical supernova while somehow leaving the star intact. The mechanism behind such massive eruptions remains one of astronomy's greatest puzzles. Some theories propose that the interaction between the two stars in the binary system creates instabilities that trigger periodic mass ejections. Others suggest that the primary star undergoes pulsational pair instability, a process where gamma rays in the stellar core create electron-positron pairs, temporarily reducing radiation pressure and causing violent oscillations. P Cygni, another famous luminous blue variable, has been observed for over 4 centuries, making it one of the longest-studied variable stars. This stellar giant underwent a major outburst in the 1600s, increasing in brightness by several magnitudes before slowly fading back to its current level. The star's distinctive P Cygni spectral profile, showing both absorption and emission features, has become a standard tool for studying stellar winds and mass loss. The Hubble Sandage variables, found in nearby galaxies, represent the most luminous stars known in the universe. These objects can shine with the brightness of several million suns, making them visible as individual stars in galaxies millions of light-years away. Their extreme luminosity places them at the theoretical upper limit for stellar masses, beyond which radiation pressure would overcome gravity and tear the star apart. Variable A in the galaxy M33 holds the record as one of the most luminous stars ever discovered, with a peak luminosity nearly 6 million times that of our Sun. This Hubble Sandage variable undergoes irregular eruptions that can change its brightness by several magnitudes over periods of years to decades, demonstrating the extreme instability of the most massive stars. The study of these hyperluminous variables in external galaxies has revealed that the upper mass limit for stars may be higher than previously thought. While theoretical models suggest that stars cannot exceed 150 to 200 solar masses, Some Hubble Sandage variables appear to have masses approaching 300 times that of our Sun LBV 1806-20, located in the Large Magellanic Cloud, represents another extreme example of stellar instability. This star has undergone multiple major outbursts over the past 2 centuries, each time ejecting significant amounts of material and creating complex nebular structures around the central object. The Spitzer Space Telescope has revealed that many luminous blue variables are surrounded by multiple shells of ejected material, indicating that these stars undergo repeated episodes of mass loss throughout their lives. These circumstellar nebulae preserve the history of stellar outbursts and provide insights into the mechanisms driving mass loss in the most massive stars. Quasi-stellar objects, or quasars, represent the most luminous persistent sources of energy in the universe, powered by supermassive black holes accreting material at prodigious rates. While not technically stars, these objects can outshine entire galaxies and provide insights into the extreme physics of matter falling into black holes. The most distant quasars, observed when the universe was less than 1 billion years old, challenge our understanding of how supermassive black holes formed and grew in the early cosmos. These ancient beacons, with redshifts exceeding 7, show us the universe when it was just beginning to emerge from the cosmic dark ages. J1342 plus 0928, one of the most distant quasars known, has a redshift of 7.54, meaning we observe it as it was when the universe was just 690 million years old. The supermassive black hole powering this quasar has a mass of 800 million suns, raising questions about how such massive objects could form so early in cosmic history. Blazars represent a special class of quasars where one of the relativistic jets points directly toward Earth, creating some of the most variable and energetic objects in the sky. These cosmic lighthouses can change in brightness by factors of hundreds over periods of hours to days, as turbulence in the jet creates fluctuations in the observed emission. 3C273, one of the first quasars discovered, remains one of the most intensively studied objects in astronomy. Located at a redshift of 0.158, this quasar has provided crucial insights into the structure and physics of active galactic nuclei. Its relativistic jet extends over 200,000 light-years from the central black hole, creating radiolobes that dwarf the host galaxy. Gamma-ray bursts represent the most energetic explosions in the universe, releasing more energy in seconds than our Sun will produce over its entire 10 billion-year lifetime. These cosmic catastrophes are thought to result from the collapse of massive stars into black holes or the merger of neutron stars, creating relativistic jets that can be detected across billions of light-years. GRB 080916C, detected by the SWIFT satellite in 2008, holds the record as the most distant gamma-ray burst ever observed, with a redshift of 8.2. This explosion occurred when the universe was just 630 million years old, providing a glimpse into the death of some of the first massive stars. The afterglow of GRB 080916C was observed by multiple telescopes across the electromagnetic spectrum, revealing the complex physics of relativistic shock waves and particle acceleration. The burst's extreme distance means that its light has been traveling for over 13 billion years, carrying information about conditions in the early universe. Long-duration gamma-ray bursts, lasting more than 2 seconds, are associated with the collapse of massive stars into black holes. The collapsar model proposes that when a rapidly rotating massive star collapses, it forms a black hole surrounded by an accretion disk. The interaction between the black hole and disk launches relativistic jets that break through the stellar envelope, creating the observed gamma-ray emission. Short-duration gamma-ray bursts, lasting less than 2 seconds, are thought to result from the merger of neutron stars or the merger of a neutron star with a black hole. The detection of gravitational waves from neutron star mergers by LIGO and Virgo has confirmed this connection, with GRB 170817A being observed just 1.7 seconds after the gravitational wave event GW 170817. Magnetars, those neutron stars with magnetic fields trillions of times stronger than Earth's, occasionally produce giant flares that can be detected across the galaxy. SGR 1806-20 produced a giant flare on December 27, 2004, that temporarily saturated gamma-ray detectors throughout the solar system and affected Earth's ionosphere from a distance of 50,000 light-years. The energy released in this single magnetar flare exceeded the total energy output of our Sun over 150,000 years, all released in just 0.2 of a second. If this flare had occurred at the distance of our nearest stellar neighbor, Proxima Centauri, it would have appeared as bright as the full moon and could have caused significant damage to Earth's ozone layer. SGR 0501+4516, another magnetar in our galaxy, has produced multiple giant flares over the past few decades. The August 27, 1998 flare from this object was so intense that it caused the night side of Earth's ionosphere to become as ionized as the day side, demonstrating the incredible power of these stellar remnants. The study of magnetar flares has revealed new insights into the physics of ultra-strong magnetic fields and their effects on matter and spacetime. The magnetic field strength in these objects approaches the quantum critical field, where the vacuum itself becomes polarized and exotic quantum effects become important. Soft gamma repeaters, a class of objects that includes magnetars, produce repeated bursts of soft gamma rays and X-rays. These objects were initially mysterious, as their burst properties didn't match those of classical gamma-ray bursts or any other known astronomical phenomenon. The connection between soft gamma repeaters and magnetars was established through detailed observations of their persistent X-ray emission and the discovery of extremely slow rotation periods. Unlike normal pulsars, which spin hundreds of times per second, magnetars rotate just once every few seconds, indicating that their rotation has been slowed by their intense magnetic fields. Anomalous X-ray pulsars represent another manifestation of magnetar physics, showing persistent X-ray emission that is too bright to be powered by rotational energy alone. The discovery that these objects also have ultra-strong magnetic fields confirmed that they are part of the same population as soft gamma repeaters. The Chandra X-ray Observatory and XMM Newton have provided detailed observations of magnetar emission, revealing complex spectral features and temporal variations that provide insights into the physics of matter in ultra-strong magnetic fields. These observations have shown that magnetar atmospheres are composed of highly magnetized plasma with properties unlike anything found elsewhere in the universe. Pulsar wind nebulae, created by the interaction between pulsar winds and the surrounding interstellar medium, represent some of the most efficient particle accelerators in the galaxy. The Crab Nebula, powered by the pulsar at its center, accelerates particles to energies exceeding those achieved in the most powerful human-built accelerators. PSR B0531+21, the pulsar at the heart of the Crab Nebula, spins 30 times per second and has a magnetic field strength of 1 trillion Gauss. The interaction between this rapidly rotating magnetized neutron star and the surrounding supernova remnant creates a complex system of shock waves, magnetic field lines, and relativistic particles. The quest to understand neutron star interiors has led to some of the most exotic physics proposals in modern science. At the extreme densities found in neutron star cores, exceeding nuclear density by factors of several, ordinary matter may undergo phase transitions to states that have never existed since the first moments after the Big Bang. Hyperon stars represent one possibility for neutron star cores, where the intense pressure converts protons and neutrons into particles containing strange quarks. Lambda, sigma, and 11 hyperons could form a significant fraction of the core material, softening the equation of state and potentially limiting the maximum mass of neutron stars. The recent discovery of 2 solar mass neutron stars has placed stringent constraints on hyperon formation, as these exotic particles would make the neutron star equation of state too soft to support such massive objects. This has led to the hyperon puzzle, reconciling laboratory measurements of hyperon interactions with astrophysical observations of massive neutron stars. Kaon condensation represents another exotic possibility for neutron star cores, where the intense matter density creates conditions favorable for the formation of kaon mesons. These particles, containing strange quarks, could form a Bose-Einstein condensate that dramatically alters the properties of neutron star matter. Color superconductivity, a phenomenon where quarks form Cooper pairs similar to electrons in conventional superconductors, might occur in the cores of the most massive neutron stars. This exotic state of matter would have zero resistance to the flow of color charge, creating conditions unlike anything found elsewhere in the universe. The transition from nuclear matter to quark matter in neutron star cores could occur through a first-order phase transition, creating a sharp boundary between different phases of matter. Alternatively, the transition might be a smooth crossover, with no distinct boundary between nuclear and quark phases. Hybrid stars, containing both nuclear matter and quark matter, represent a compromise between these extreme possibilities. These objects would have nuclear matter in their outer cores and quark matter in their centers, with the transition occurring at densities several times nuclear density. The study of neutron star cooling has provided indirect evidence for exotic matter phases through observations of rapid temperature drops in young neutron stars. The enhanced cooling observed in some objects suggests the presence of exotic particles that provide additional cooling mechanisms through neutrino emission. Pulsar glitches, sudden increases in neutron star rotation rates, provide insights into the structure of neutron star crusts and the coupling between different components of these objects. The Vela pulsar undergoes major glitches every few years, suddenly spinning up by parts in a million before gradually returning to its previous rotation rate. The largest pulsar glitch ever recorded occurred in PSR J0537-6910, where the neutron star suddenly increased its rotation rate by parts in 100,000. This enormous glitch suggests that young, rapidly rotating neutron stars can store vast amounts of rotational energy in their crusts before releasing it catastrophically. Timing arrays using networks of millisecond pulsars have begun to detect the gravitational wave background from supermassive black hole mergers throughout the universe. These observations represent the first detection of gravitational waves at nanohertz frequencies, opening a new window into cosmic evolution and structure formation. The North American Nanohertz Observatory for Gravitational Waves and similar international collaborations monitor dozens of millisecond pulsars with nanosecond timing precision, searching for correlated timing variations that would indicate passing gravitational waves. These natural gravitational wave detectors complement ground-based observatories like LIGO and Virgo. Fast radio bursts represent one of the most mysterious phenomena in modern astronomy. Brief, intense pulses of radio emission that appear to come from cosmological distances. These millisecond duration events release as much energy as our sun produces in several days, yet their origin remains hotly debated. FRB 121102, the first repeating fast radio burst discovered, has provided crucial insights into these enigmatic events. Located in a dwarf galaxy 3 billion light-years away, this source has produced hundreds of bursts with varying properties, suggesting a complex emission mechanism. The discovery that some fast radio bursts repeat, while others appear to be one-time events, has led to proposals for multiple formation mechanisms. Magnetar giant flares, neutron star mergers, and exotic stellar explosions have all been proposed as possible sources for these cosmic radio beacons. SGR 1935 plus 2154, a magnetar in our galaxy, produced a fast radio burst-like event in April 2020, providing the first direct evidence linking these phenomena to magnetars. This discovery suggests that at least some fast radio bursts originate from highly magnetized neutron stars. The polarization properties of fast radio bursts reveal that they propagate through highly magnetized environments, consistent with emission from magnetars or other neutron star phenomena. The rotation measure, a quantity that depends on magnetic field strength and electron density, shows extreme values for many fast radio bursts. Soft gamma repeaters in nearby galaxies have been proposed as possible sources for some fast radio bursts, as giant flares from these objects could produce the observed radio emission through coherent emission mechanisms. The detection of radio emission from the December 27, 2004 giant flare supports this connection. The study of fast radio burst host galaxies has revealed that these events occur in a wide variety of environments, from massive elliptical galaxies to small star-forming dwarf galaxies. This diversity suggests that multiple formation mechanisms may be responsible for the observed population. Dispersion measure analysis of fast radio bursts provides a new tool for studying the intergalactic medium and measuring cosmological parameters. The time delay between different radio frequencies caused by free electrons along the line of sight can constrain the baryon content of the universe. FRB 180916, with a dispersion measure exceeding 1500 parsecs per cubic centimeter, represents one of the most distant fast radio bursts detected. This event, originating from a galaxy over 4 billion light-years away, demonstrates that these phenomena can be observed across a significant fraction of the observable universe. The energy requirements for fast radio bursts at cosmological distances are truly staggering, requiring coherent emission mechanisms that can convert significant fractions of available energy into radio waves. The brightness temperatures inferred for these events exceed 10 to the 35 Kelvin, far higher than any thermal emission mechanism could produce. Coherent curvature radiation from relativistic particles moving along magnetic field lines represents one promising mechanism for fast radio burst emission. This process, which also operates in pulsar radio emission, could be amplified in the extreme magnetic field environments around magnetars. Plasma instabilities in magnetar magnetospheres could create the conditions necessary for coherent radio emission, with the intense magnetic fields providing the energy source and the plasma dynamics creating the coherent emission mechanism. The complex interplay between magnetic fields, plasma physics, and relativistic effects makes these systems natural laboratories for extreme physics. The connection between fast radio bursts and gamma-ray bursts remains an active area of research, with some models proposing that both phenomena result from similar physical processes operating under different conditions. The detection of gamma-ray emission coincident with some fast radio bursts supports this connection. Neutron-star black hole mergers represent another possible source for fast radio bursts, as the disruption of neutron-star magnetospheres during the merger process could create the conditions necessary for coherent radio emission. The recent detection of gravitational waves from such mergers provides new opportunities to test this hypothesis. The study of fast radio burst environments through absorption line spectroscopy has revealed complex gas structures around these sources, suggesting that they occur in regions of active star formation or stellar feedback. These observations provide insights into the local environments where fast radio bursts originate. Scintillation effects in fast radio burst signals, caused by turbulence in the interstellar and intergalactic media, provide additional tools for studying these phenomena and their propagation through cosmic plasma. The frequency-dependent intensity variations can constrain the size and structure of the emission regions. The development of new radio telescopes specifically designed for fast radio burst detection has revolutionized the field, with facilities like CHIME, ESCAP, and the Future Square Kilometer Array promising to detect thousands of these events and transform our understanding of their nature and origin. Real-time detection and localization of fast radio bursts has enabled rapid follow-up observations across the electromagnetic spectrum, searching for counterparts that could provide additional clues about their physical origin. The combination of radio, optical, X-ray, and gamma-ray observations promises to unlock the secrets of these cosmic enigmas. The statistical properties of fast radio burst populations, including their rate, energy distribution, and spatial clustering, provide constraints on formation models and the underlying physics responsible for these phenomena. Large samples of well-localized events will be crucial for distinguishing between competing theoretical models. The search for periodic fast radio bursts has revealed that some sources exhibit complex temporal patterns that challenge simple emission models. FRB 180916.J0158+65, discovered by the CHIME telescope, shows a 16-day activity cycle where bursts occurred during a 4-day window followed by 12 days of silence. This periodic behavior suggests that fast radio burst emission might be modulated by orbital motion in a binary system, precession of neutron star magnetic fields, or other cyclical processes. The discovery of periodicity provides crucial constraints on emission models and the nature of fast radio burst progenitors. The intensity distribution of fast radio bursts follows a power law relationship, with most events being relatively weak, while a few reach extraordinary brightness levels. This statistical behavior resembles that seen in solar flares, earthquake magnitudes, and other phenomena governed by self-organized criticality. FRB 200428, detected by the CHIME telescope, reached a peak flux density exceeding 60,000 Janskis, making it one of the brightest radio sources ever observed. This extraordinary event demonstrates that fast radio burst emission mechanisms can achieve remarkable efficiency in converting energy to coherent radio waves. The morphology of individual fast radio burst pulses reveals a complex substructure that provides insights into the emission physics. Some bursts show multiple components separated by milliseconds, while others display smooth, single-peaked profiles that suggest different emission mechanisms or source geometries. Downward frequency drift, observed in many fast radio burst pulses, indicates that higher frequencies arrive before lower frequencies, the opposite of what would be expected from simple dispersion effects. This sad trombone effect suggests that the emission mechanism itself has frequency-dependent timing, possibly related to plasma physics in the emission region. The discovery of fast radio bursts at frequencies below 400 MHz has extended the observable frequency range and provided new constraints on emission models. Low-frequency observations are particularly sensitive to scattering effects and can probe different aspects of the emission physics. Scattering tails in fast radio burst pulses, caused by multipath propagation through turbulent plasma, provide information about the environments surrounding these sources. The scattering timescales can constrain the density and structure of ionized gas in fast radio burst host galaxies and the intergalactic medium. The polarization properties of fast radio bursts reveal highly organized magnetic field structures in their emission regions. Linear polarization fractions approaching 100% indicate coherent emission processes, while circular polarization provides additional constraints on the magnetic field geometry and plasma conditions. Faraday rotation, the rotation of polarization angle caused by propagation through magnetized plasma, reaches extreme values in some fast radio bursts. Rotation measures exceeding 100,000 radians per square meter suggest magnetic field strengths and electron densities far higher than typical interstellar values. The study of fast radio burst host galaxy properties has revealed correlations between burst properties and galactic environments. Bursts from massive, metal-rich galaxies tend to have different characteristics than those from small, star-forming galaxies, suggesting that progenitor properties depend on galactic evolution and stellar populations. Gravitational lensing of fast radio bursts by intervening galaxies and galaxy clusters could create multiple images of the same event, arriving at different times and with different magnifications. The search for lensed fast radio bursts represents a new frontier that could provide insights into dark matter distribution and cosmological parameters. The use of fast radio bursts as cosmological probes depends on understanding their intrinsic properties and correcting for propagation effects. The dispersion measure-redshift relationship could provide an independent method for measuring the Hubble constant and constraining dark energy properties. Machine learning algorithms have revolutionized fast radio burst detection and classification, enabling real-time identification of these brief events in the vast data streams produced by modern radio telescopes. Artificial intelligence systems can now detect and characterize fast radio bursts faster than human observers. The development of interferometric techniques for fast radio burst localization has improved position accuracy from degrees to arcseconds, enabling identification of host galaxies and detailed studies of burst environments. Very long baseline interferometry promises even higher precision localization for the brightest events. Simultaneous multi-wavelength observations of fast radio burst sources have searched for counterparts across the electromagnetic spectrum, from gamma rays to optical wavelengths. While most searches have yielded null results, the few positive detections provide crucial insights into the emission physics. The connection between fast radio bursts and other transient phenomena continues to be explored through coordinated observing campaigns. The temporal coincidence of fast radio bursts with gamma-ray bursts, gravitational wave events, or neutrino detections could reveal fundamental connections between different high-energy astrophysical processes. Population synthesis models attempt to explain the observed fast radio burst rate and properties through detailed simulations of stellar evolution and neutron star formation. These models must account for the birth rate of potential progenitors, their evolution over cosmic time, and the efficiency of fast radio burst production. The energy budget problem for fast radio bursts at cosmological distances requires emission mechanisms that can convert significant fractions of available energy into coherent radio waves. Magnetic reconnection, plasma instabilities, and coherent emission processes all face challenges in achieving the required efficiency. Repeating fast radio bursts show evolution in their burst properties over time, with changes in peak frequency, bandwidth, and temporal structure. FRB 121102 has exhibited systematic changes in its emission properties over several years of observations, suggesting evolution in the source environment or emission mechanism. The clustering of fast radio burst arrival times in some repeating sources indicates that the emission process is not purely random, but may involve triggering mechanisms or memory effects. Statistical analysis of burst timing can constrain models for the underlying emission physics. Environmental effects on fast radio burst propagation include scattering by turbulent plasma, absorption by intervening material, and frequency-dependent delays caused by dispersion. Understanding these effects is crucial for interpreting observed burst properties and inferring source characteristics. The search for fast radio burst precursors and afterglows has yielded few positive results, suggesting that most of these events are not associated with long-lived emission at other wavelengths. This places constraints on models that invoke accretion processes or sustained magnetic activity. Plasma lensing effects, caused by density fluctuations in the ionized interstellar medium, can focus or defocus fast radio burst emission, creating apparent brightness variations that are not intrinsic to the source. These effects must be considered when interpreting the observed intensity distributions. The development of next-generation radio telescopes specifically optimized for fast radio burst science promises to increase detection rates by orders of magnitude. The Square-Kilometer Array, when completed, will detect thousands of fast radio bursts per day and revolutionize our understanding of these phenomena. Real-time fast radio burst detection systems enable rapid alerts to other observatories, facilitating multi-wavelength follow-up observations within minutes or hours of burst detection. These coordinated campaigns maximize the scientific return from each detected event. The study of fast radio burst polarization evolution during individual pulses provides insights into the magnetic field structure and plasma conditions in the emission region. Time-resolved polarimetry can reveal rotation measure variations on microsecond timescales, constraining the size and dynamics of the emission region. Coherent de-dispersion techniques allow astronomers to correct for the frequency-dependent delays caused by free electrons along the line of sight, revealing the intrinsic temporal structure of fast radio burst pulses. These methods are essential for studying the shortest duration events and finest temporal details. The search for fast radio burst periodicity on longer timescales continues to yield new discoveries, with some sources showing evidence for activity cycles lasting months or years. These long-term patterns could be related to binary orbital motion, precession cycles, or other slowly varying physical processes. Artificial intelligence and machine learning continue to play increasingly important roles in fast radio burst research, from real-time detection algorithms to sophisticated classification schemes that can identify different types of bursts and predict their properties. These tools are essential for handling the enormous data volumes produced by modern radio surveys. If you made it this far, make sure to subscribe to the channel and give a like. And check out this other video at the left side of the screen. What would really happen if you traveled at light speed? In this video, we break down the mind-blowing science behind light speed travel, time dilation, and Einstein's special relativity. See you there.